Today we are learning how to describe and characterize biaxial minerals. Our goal is to determine the optic sign and the 2V angle for a given biaxial mineral. Step 1. In cross-polarized light, pick a grain with low retardation of a given mineral. Step 2. Center your grain, switch to the highest objective, and focus. Step 3. Insert the Bertrand lens and the condensing lens. For this microscope, the switch labeled BL inserts both. This is the interference figure we have obtained. The extinct arm is called an isogyre. Although we only see one isogyre in this field of view, it is important to note that all biaxial minerals have two isogyres. The interference color bands circling the isogyre are called isochromes. The center, or elbow of the isogyre, is where there is an optic axis. This is called a melatope. Since we have two isogyres, we have two optic axes. This is where we get the term biaxial mineral. This is known as the optic axis-centered biaxial interference figure. Step 4. Rotate your stage such that the inside of the curve of the isogyre wraps around the southeast quadrant. Step 5. Note the interference colors both outside and inside the curve of the isogyre. Here, both sides have a range in first-order isochromes. We see white, yellow, and magenta interference colors appear in that order. Step 6. Insert the accessory plate and observe the changes. Here, our example shows an increase in retardation inside the curve of the isogyre and a decrease in retardation outside the curve of the isogyre. Step 7. Compare to optic sign charts. In a biaxial negative mineral, we see an increase inside the curve of the isogyre and a decrease outside. In a biaxial positive mineral, we see a decrease on the inside and an increase outside. It is important that we align the isogyre as pictured because it needs to correlate to the direction that we insert the accessory plate. This example is a biaxial negative mineral. Next, we will determine the 2V angle. This is the angle between the two optic axes. We can determine the angle by examining the curvature of the isogyres. Step 8. Compare curvature to chart of 2V angles. Notice in the diagram that the 2V angle ranges from a straight line at 90 degrees to sharp right angles at 0 degrees. When the 2V angle goes to 0, the two optic axes merge into one, giving rise to a uniaxial material. This mineral has a 2V angle between 60 degrees and 75 degrees. Let's try an example together. Here, I start in cross-polarized light. As I rotate the stage, pick out what you think is the best grain to use. This grain in the center has the lowest retardation, so we should use that. Next, I will switch to the highest objective, focus, and then insert my Bertrand lens and my condensing lens. As I rotate the stage, observe the isogyres. Note that you can see both isogyres here, unlike our last example. Here, I orient my isogyre so that it curves around the southeast quadrant. Take note of the interference colors now. Next, I will insert the accessory plate. Observe the changes for yourself. What is the optic sign of this mineral? If you said biaxial negative, you are correct. The area under the curve of the isogyre exhibits an increase in interference colors, and the area outside of the curve exhibits less of an increase. Now, let's determine the 2V angle. What do you think? Our isogyres are much more curved than the previous example, so the 2V angle is between 15 degrees and 30 degrees. Here are some things to remember and some helpful tips. Try to find the lowest interference color of your mineral. Most biaxial interference figures are not perfect. Be patient finding the right grain and the isogyres. Try to orient your curve so that the elbow is in the center of your field of view and is always curving around the southeast quadrant. The reference circles provided are only for microscopes where a gypsum accessory plate is inserted from the southeast.